This video is based on chapter 6.1, the nature of energy. And let's begin with just a whole bunch of definitions. What is energy? Energy is defined as the capacity to do work or to produce heat. So if a system has a certain amount of energy, that's how much it can be used to do work or produce heat. The law of conservation of energy, you've probably heard of before, simply says that energy can be converted from one form to another, but it cannot be created or destroyed. Related to that is the first law of thermodynamics, which says that the energy of the universe is constant. Potential energy is energy due to position or composition. Kinetic energy is energy due to motion, and we can calculate kinetic energy by simply multiplying the mass of the object by the square of the velocity and dividing by 2. Now, I'll talk in a minute about how potential energy and kinetic energy can be converted to one another, but let's talk for a minute about units. Okay? The SI unit of mass is kilograms, the SI unit of velocity is meter per second, so that tells us the SI unit of energy is kilogram meter squared per second squared, which we'll get to later. Here's a diagram that shows how potential energy and kinetic energy can be interconverted. If a bicyclist at the bottom of the hill is moving rapidly, he or she has kinetic energy. As they go to the top of the hill, they decrease their kinetic energy because they're slowing down, but they increase their potential energy because they're further from the center of the earth. At the top, when the bicycle stops moving, there is zero kinetic energy. It's all been converted to potential energy. But when the bicyclist starts rolling down the hill, the potential energy decreases as it is being converted to kinetic energy. Heat is a form of energy that is transferred from one system to another due to a difference in temperature. So if I imagine two objects next to each other, the one on the left is at temperature T1, the one on the right is temperature T2. If T1 is greater than T2, then heat energy will spontaneously flow from the object on the left to the object on the right, and when they reach the same temperature, we have achieved what's called thermal equilibrium. Work is energy expended when a force is exerted over a distance. And to calculate the amount of work that's done in a process, you simply multiply the force by the distance. Now, this leads to a very important concept, which is that of a state function or a state property. And this is defined as a property that depends only on the present state of the system, and a change in a state function depends only on the initial and final states. It does not depend upon the pathway. We'll get to this later in the chapter. It's going to be very important, as you'll see. Okay? For an example, if I were to carry a heavy object from the basement to the third floor, I could take a variety of different pathways. I could go directly up the steps, I could stop on the first floor, I could run around on the first floor, and then carry it up to the second floor. The elevation, that is the difference in height between the basement and the third floor, is a state function because all that matters is the initial state and the final state. But the work that I do is not a state function, it is dependent upon the pathway. Now, let's talk about energy in chemical processes. Okay? Did you know that the universe is divided into two parts? The system and the surroundings. Okay? I'm going to consider the combustion of 1 mole of methane to be the system, and everything else is in the surroundings. This is what's called a potential energy diagram, and it shows the relative potential energies of reactants and products. As you can see, carbon dioxide and water, the products of the combustion, are at a lower potential energy than the reactants, methane and oxygen. So that means when the process occurs, when the reaction takes place, there is a decrease in potential energy, which is released from the system to the surroundings. Okay? This is referred to as an exothermic process. Energy flows from the system to the surroundings. For this process, delta E, the change in energy, is going to be negative because the final energy is lower than the initial energy. On the other hand, we could have a chemical reaction in which the potential energy of the reactants is lower than the potential energy of the products. Again, the reaction, in this case the combustion of 1 mole of nitrogen to form 2 moles of nitrogen monoxide. In this process now, heat energy must flow from the surroundings to the system in order for it to take place. This is referred to as an endothermic process. Energy flows from the surroundings to the systems, and in this case, delta E is negative. So just to reiterate, everything is from the system's point of view. Okay? So if I have heat energy flowing from the system to the surroundings, delta E is negative. If, on the other hand, I have energy flowing from the surroundings to the system, delta E is positive. Okay? And again, I can't emphasize strongly enough, Delta E is determined from the point of view of the system because the change in energy is always the final energy state after the process minus the initial energy before the process. The internal energy of the system is defined as the sum of the kinetic and potential energies of all the particles in the system. And we never actually calculate the absolute energy of a system. What we're concerned with is delta E, the change in total internal energy. Okay? And this can be calculated using a very simple process. Delta E equals Q plus W. Q is defined as the heat flow. W is the work done. What are the units? Well, as I said before, the units on both are joules. And 1 joule, as I said, is 1 kilogram meter square per second square. Again, the sign convention is always considered from the system's point of view. If heat flows from the system to the surroundings, the system is losing heat energy, so Q is negative. If heat flows from the surroundings into the system, Q is positive because the system is gaining heat energy. If work is done by the surroundings on the system, that is, if a force is exerted through a distance from the surroundings onto the system, W is positive because the system is gaining energy in the form of work being done on it. But if work is done by the system on the surroundings, work energy is flowing from the system into the surroundings. It is losing energy by doing work on the surroundings, so W is negative. Let's do a simple calculation. If the internal energy of the thermodynamic system is increased by 300 joules, while 75 joules of expansion work is done, how much heat is transferred and in which direction to or from the system? So we'll start by writing our equation. Delta E equals Q plus W. Delta E, because the internal energy is increasing, we'll say delta E is positive 300 joules. If the system is expanding, that means the system is doing work on the surroundings. It is losing energy by doing so, so the work is going to be negative 75 joules. To solve for Q, Q equals delta E minus W equals plus 300 joules minus negative 75 joules, or Q is equal to positive 375 joules, and this is gained by the system from the surroundings. Let's talk about a particular type of work. It's called PV work, where P stands for pressure, V stands for volume. This is work done when a gas changes volume against a constant pressure. Let's look at a diagram. Okay. On the left, I see a sample of gas that has a certain initial volume, V1. The external pressure exerted on it is constant. The volume of the gas decreases to the final volume, the height difference being H final minus H initial, or delta H. So the volume change, delta V, is the surface area of the top of the piston times delta H. Now, to calculate how much work is done in this process, let's do some derivations. You're not responsible for this derivation, by the way, but I want you to see it. The work done is force times distance, which is force times delta H being the height difference. Pressure is force over area. So I can rearrange this to write force equals pressure times area. Work, which we said is force times delta H, now becomes pressure times area times delta H. Delta V, the final volume minus the initial volume, we said is area times delta H. So substituting, that gives me work equals pressure times area times delta H, or pressure times delta volume, or summing it up, work equals negative P delta V. Okay? Negative because, as we said, if work is being done by the surroundings on the system, okay, delta V is going to be negative. Negative times a negative gives me a positive, so work ends up being positive, which is must be the case if work is being done by the surroundings on the system. So let's finish with a simple problem. A sample of gas enclosed in a cylinder with a piston at constant temperature expands from 10 liters to 25 liters against a constant pressure. If the total energy change is negative 160 liter atmospheres, and in the process the gas absorbs 50 liter atmospheres of heat energy, against what pressure did the gas expand? Well, there's a lot going on here, but let's just start with what we know. We know the total change in energy equals Q plus W. We know work equals negative pressure times change in volume, and change in volume equals final volume minus initial volume. My final volume is 25 liters. My initial volume is 10 liters. Delta E equals negative 160 liters times atmospheres. Q, because the gas absorbed 50 liter atmospheres of heat energy, this must be positive, is plus 50 liter atmospheres. And we are trying to solve for the pressure. Well, let's do some substitution. We'll rearrange. Delta E equals Q, sorry, number 4. Where's my eraser? There's the eraser. So delta E equals Q minus P delta V is equal to Q minus P times final volume minus initial volume, or pressure times final volume minus initial volume is Q minus delta E, or solving for pressure, pressure equals Q minus delta E over final volume minus initial volume, and now I can plug in. Q is plus 50 liter atmospheres minus negative 160 liter atmospheres, all divided by 25 liters minus 10 liters, or pressure is 210 liter atmospheres over 15 liters, or 14 atmospheres as my pressure. Now you may be wondering, how is pressure times volume a unit of energy? It is, and I will explain that in class.